In this question, we're going to have a look at chemical equilibrium, and we're going to have a look at the 2010 paper, higher level paper, question 7. It was a full question in 2010, chemical equilibrium. You can see here that they've started the question by giving you an equation. They've asked the first couple of questions on it are theory, and then we've got a little bit of calculations and then more theory towards the end. So for the first two questions, I'll just do orally. This is a reversible reaction. So we've got phosphorus 5 chloride decomposes into phosphorus 3 chloride and chlorine at a temperature of 500 Kelvin according to the following balanced equation. So you've got your phosphorus 5 chlorine, your phosphorus 3 chlorine, and here's some chlorine. This is a reversible reaction and a dynamic equilibrium is reached. Explain the underlying terms and why is the equilibrium described as dynamic for 11 marks. So I suppose a reversible reaction is one that can go forwards or backwards. This reaction can go forwards or backwards. And equilibrium is reached. So that is a point where the forwards reaction is equal, the rate of the forwards reaction is equal to the rate of the backwards reaction. So they kind of appear to settle in terms of the concentrations of each of the three species. So you end up with a balanced amount of each three, which appears like it's stopped, I suppose, really. But it's described as dynamic. And why is it dynamic? It's dynamic because it's constantly going. So it's constantly going forwards, constantly going backwards, constantly forwards and backwards. You've got this dynamic equilibrium for 11 marks to describe the three of those words, really. Then on to part B. There's 12 marks for part B, probably 6 marks for the first part and 6 for the second part. State Le Chatelier's principle. So Le Chatelier's principle, you should know at this stage, is that when a stress is applied to a system at equilibrium, that the position of equilibrium will adjust to relieve the stress. So basically the position of equilibrium adjusts to relieve the stress. So that is in relation to these reactions that are reversible and that are in a state of equilibrium. Write the equilibrium constant Kc for the expression for the above reaction. So I'll just go through this. 6 marks for it. I've written down this is question 7. And if we're looking at the equilibrium constant expression, you just say PCl3, Cl2, put them in square brackets, put them to the power of whatever's in front of them. In this case, there's only a 1, so no need to put in any power. And the reactant below the line, again to the power of whatever's in front of it, which in this case is a 1. So no need to do anything there. You can see it fully there now. And that's the answer for 6 marks for part B. Okay, moving on into part C. If you see this, part C says that when 208.5 grams of phosphorus 5 chloride is heated in a 100-liter container at a temperature of 500 Kelvin, equilibrium is established with 53.25 grams of chlorine gas present in the container. Calculate the value of the equilibrium constant Kc for the reaction at 500 Kelvin for 12 marks for this part. So this is the calculation part where you're going to have to go and do at the start, your table, then used/formed is what I like to do, and then you go at equilibrium, EQUILIB, and then we'll go per liter as well, because this is in a 100-liter flask, it says. So we'll divide it all by 100 to get it per liter. Some of the other questions that we looked at, they were in 1-liter flasks. So for that reason, you don't need to divide by 1. So if we look at the question that it has, the data that they've given us in the question, 208.5 grams of phosphorus 5 chloride. So when we're given a grams, we're going to have to turn that into moles. Same here with the chlorine. We've been told that there's 53.25 grams of chlorine gas. And we're going to have to get that into moles. And we go from grams to moles by dividing by the MR. Again, I'll just use the right hand side over here. So if we're talking about PCl5, I'll just look up the values of these in a periodic table. Chlorine is 35.5, so you need 5 of those. And phosphorus is 31, so just the one of those. When you add these up, you get 208 as the mass of 1 mole of it, the relative molecular mass. So that's the answer for the MR of PCl5. Now we've been told that there's 208.5 grams. So what we're going to do is 208.5. We're going to divide that by 208.5. Works out quite nicely that there is 1 mole of PCl5 in the vessel at the beginning. Now we've got none of this at the beginning and none of this at the beginning because we just started with the phosphorus 5 chloride. Now if you go on to the second row here, used/formed. Used is subtracted, formed is added. And I use the numbers in front of the species to figure out the ratio of what's used and formed. In this case, it's just a 1x. And in this case, again, it's just 1x. Just a 1 in front of the PCl3. Just a 1 there in front of the Cl2 as well. So 1x. All the ways across the board. So at equilibrium, what we should find is that the formed side, the products, should be 0 plus x, which would give us x, and 0 plus x. And the reactant side would be 1 minus x, because we subtract the used amount from the amount at the beginning. So that's where we get to. Now, the other value that we have been given here in the question is the amount of chlorine gas present, 53.25 grams. So, and that's the chlorine here, 53.25, and we're going to have to divide that by the MR of chlorine, Cl2. It's 35.5 for one of them. We're going to multiply it by 2, we're going to get 71. So we divide this by 71. And the answer that we get for that is 0.75. So 0.75 is the number of moles that we have at equilibrium here of the chlorine. Now that's actually told us what the x is. The x is 0.75. So this is also going to be 0.75, and this is going to be 1 minus 0.75, which will give us 0.25. So that gives us the different values there of the 3 different species at equilibrium. So the next thing that we're going to have to do is we're going to have to establish the value per litre, because this is in a 100 litre vessel. So we're going to have to divide each of these 3 values by 100. So we'll get 0.0025. We got 0.0075, 0.0075 there as well. Now, the next thing that we're going to do is we're going to slot these values into our Kc expression. So our Kc expression is going to look like this: 0.0025 No, that's below the line actually. So it's 0.0075 above the line. Multiplied by 0.0075. They're the 2 values from here that go above the line. And then below the line, we put 0.0025. And they're not to the power of anything, because there is no value in front of them. So we're going to put 0.0075 multiply by 0.0075, and then we're going to divide that by 0.0025, and the answer that we get is 0.0225. Okay, you don't have to do this, but what you can do is you can put in the units. They don't tend to take away marks if you leave out the units. They just ask for the value. But if you were to put in the units, you can see that this is moles per liter, this is moles per liter, and this is moles per liter, and one of them cancels with one of the others. So the units are actually, in this case, moles per liter. So that is the answer there for part C. Going on to part D. This is C for 12 marks. On to part D. When the temperature of the equilibrium mixture is increased, the phosphorus 5-chloride decomposes further. Is this an endothermic reaction or an exothermic reaction? So when the temperature is increased, it moves forward. Okay, so that would suggest to me that the heat is on the left hand side, because if you increase the heat, it'll move away from the stress. So that would suggest that this is heat on the left hand side, and heat on the left hand side would mean that it's endothermic. And give you a reason for your answer. Well, you can say that Le Chatelier's principle says that when a stress is applied, the equilibrium moves away to adjust for the stress, and in this case, if you're heating it up and it's moving forward, it suggests that the forwards reaction is endothermic. And then the last part, part E. Part E is looking at what change, if any, would an increase in the pressure have on the value of Kc? Well, if you are looking at this, we've got one species here on the left, we've got two on the right, and if you increase the pressure, it'll move towards the left, because it'll go to the side which has fewer particles. There's two molecules here on the right. On the left there's only one. So increasing the pressure would make it go to the left, and that would give us the result of having a lower Kc. Increasing pressure moves the equilibrium to the left, so the Kc becomes smaller. And that is the 2010 higher level question in its entirety.